when I want to optimize something, I want to make it the biggest it can be, but potentially also I could go the other way and want it the smallest it could be. So that two types of problems I'm going to look at: making something as big as it could be or as small as it could be, depending upon what makes sense in the context of the problem. So that optimizing, that's what that means. Make it the best it can be, whether that be the maximum or the minimum. In some cases, you may want to minimize it for various reasons, okay? So that's what we're talking about here, is optimization problems. Now, why are we talking about it now? Well, we've just gotten through, a couple of days ago anyway, talking about maxes and mins. So if I want to make something as big as it can be, I'm looking for its maximum. Or if I want to make something as small as it could be, I'm looking for its minimum. So that's why the tie-in now. Optimization, we're going to find a maximum or a minimum, and we're going to use our techniques that we previously learned about. Okay? All right, so number one, what is the maximum area? On the handout there provided you, talk about the maximum area for a rectangle with perimeter P equals 400 feet. I want to maximize the area that I can generate with a rectangle, perimeter 400 feet. Okay. So, a lot of times it might be good, first step, to draw a picture. This one would be very simple, so may not be that necessary, but we're talking about a rectangle. And on a rectangle, I've got two dimensions, a length and a width, L and W. So we'll go with that picture there. Like I said, that you know what a rectangle is and what it looks like, but a lot of times this first step, so I'm just kind of doing step by step how these usually work. Draw the picture if it helps. All right. Now, step two here is I need a formula. And actually, there's going to be a couple of formulas here in this particular case, but what I want to maximize is I want to maximize the area. So definitely I need an area formula, and like I said, this one's a fairly simple one. The formula is just length times width. And so I want to maximize that. Now, I'm looking for that maximum. Previously, when we were finding maximums of a function, what did we do? Where was the maximum value? How did I find those maximum values from a function? Like if I have f of x equals whatever it is, x cubed minus 7x squared plus 8x minus 10. How did I find the maximums or minimums? Critical numbers, right? I did the derivative, and then I set the derivative equal to 0, potentially does not exist, where the derivative does not exist. I look for the derivative, and then the derivative equals 0 in most cases. Same thing here. I'm going to do the derivative of this. Now the problem is I just know right now how to do critical numbers with one variable functions. In this particular case, I've got a two variable function, and that's kind of messing me up for the time being. And so that's why I'm saying there's usually a second equation that you use, and in this case, it's the perimeter equation, the perimeter of a rectangle. So that second equation is going to help me fix the two variable problem here. The perimeter of a rectangle, different forms of it, but 2L plus 2W, perimeter is just all the sides added together, L, W plus L plus W. 2L plus 2W, perimeter of a rectangle. Well, I just so happen to know that the perimeter I want is 400, so let's substitute that in also. And look what I can do here. What I can do now is I can solve this equation for one of the variables, and it doesn't matter in this case, and plug that back into this one. So I'm going to solve this for L or W, doesn't matter. It's just big W. Let's solve that one for W. So subtract 2L and then divide by 2. And we got W equals 200 minus L. Simplifies really nicely there. Okay? Just pick one of the variables to solve for. Sometimes one's easier than the other. In this case, there wasn't much of a difference there. So, not any difference, actually. But now I can substitute this back in the other equation. Right? Because this is saying W equals 200 minus L, so I can substitute that for W in the other equation. See what I'm saying? So I get A now equals L times 200 minus L. Now I'm in good shape because I know how to do maximums on this. It's just the same as that. Find the critical numbers and that'll give you your maximum or minimum depending upon function. Okay? Now, if I leave it as is, that would be product rule. So let's go ahead and multiply it out. Make the derivative a little easier. 200L minus L squared. So yeah, here's what we're, the maximum is going to occur at the critical number. At a critical number. Like I said, it's max or min. In this case, the max. And how do I get critical numbers? Usually derivative equals 0. So I need to get the derivative and set that equal to 0. With me there? So what's the derivative? Derivative is 200 minus 2L. Critical number, so I'll set that equal to 0. The critical number here. Subtract 200, divide by -2, however you want to do it. L equals 100. What is the maximum area? Well, that's the length of the thing that gives me the maximum area. Okay? So this L is 100 is where I would have a maximum area. It's where the area is maximum. So the maximum area would just actually be length times width. So that's telling me the maximum area is going to be length is 100. Now I need the width to go with that. Well, if the length's 100, then what's the width? So W is 200 minus L. So in this case, W would be 200 minus 100, which is also 100, isn't it? So the maximum area is going to be 100 times 100. 10,000 square feet. Okay? Now you might have known that, you know that fact. If you've got a rectangle, the maximum area you can have for a rectangle is a square. That's always true. So if you knew that fact going in, you probably could have guessed the answer here, but yeah, the maximum area for a full rectangle is always a square. That's as big as an area you can get, because a square is just a special rectangle. But the square maximizes that area of the rectangle. If now we'll make a few little tweaks to that, but you can't always use a square, actually. But the problems will do. But in this problem, it's always a square. Okay? But that's just a side note. Now, number 2. Is that okay? Any questions on that? Number 2. Suppose a fence is to be constructed along a river. Fence along a river. And it's going to enclose a rectangular area. summarize here. No fencing will be put along the river. So, okay, so let me just draw the picture and then I'll fill in the rest of the details. All right, so I've got a river and I'm going to put a rectangular fence around it, but there's no fencing along the river. We'll give the livestock or whatever it is access to the river. Okay, so that's, like I said, a diagram helps in some cases. All right, if 200 feet of fencing is used, so I've got fencing is 200 feet. 200 feet of fencing. What's the maximum area that can be enclosed? All right, well, again, we've got a rectangle, and I want to maximize the area. Same formula, isn't it? I've got length and a width, so the area formula, it's the same one as number one, length times width, because it's still just a rectangular area. However, in this case, I'm not going to use the full perimeter formula because I want to tie this into the fencing, and so my second equation is the fencing equation. And what would be the fencing equation here? How much fence do I have? What if I added up all the fences there? Well, I've got a W plus an L plus a W. That's 2 W's plus 1 L. By my diagram. Yes? And I know the fencing is 200, so it's 200 equals 2W plus L. Okay? So those are my equations. Now what I'm going to do with it. This is what I want to maximize. Right? And the maximum is going to occur at the critical number, derivative equals 0, usually. But the problem is 2 variables. So I need to get this down to 1 variable. That's where this equation comes in. Solve that for one of the variables. Now in this case, it makes more sense. I mean, you can do it either way you want, but it makes more sense here to solve for L, doesn't it? So let's subtract 2W, and that equals L. Now I can substitute that for my L in the original equation. Gives me A equals 200 minus 2W times W. Yes? With me so far? Okay? I want to maximize that. Well, I know the maximum usually occurs at that critical number. Derivative equals 0. So let's take the derivative of this. But I would say, instead of having to use the product rule, let's multiply this out. Make it 200W minus 2W squared. And that makes the derivative so much easier, right? It would just be 200 minus 4W. I want the critical number, so I want that set equal to 0. I'm going to add 4W. 200 would equal 4W, so you add 4W. And then divide by 4, W equals 50. So what does that make the maximum area? Well, maximum area, I now know the W is so it would be a length times a width, but I now know the length is 50. Previous problem, the length was 50, but is that the case here? No, the length is 200 minus 2L, 200 minus 2W. And so that's 200 minus 2 times 50 is 200 minus 100, that's 100. Yeah, the length here is 100, not 50. So that's what I'm saying. That square thing only works for the full perimeter rectangle. So the maximum area is 5,000. Is this feet to each square? Yeah, feet square. Good. So there's no area bigger than that I could get. Try any other length or width you want. That's the maximum I could get. Okay? Now we haven't, might stay here, I haven't shown that it's a maximum here, but in the context of the problem, that's what I'm going to find. you know, we could do our little chart thing here, the second derivative test, you know, plug in 50 and then, you know, test our derivative on either side, a prime at 0 and a prime at 51. You know, I could do that just to prove it. Well, 0 wouldn't be a good one, but yeah, 0 would be good. Because that would be 200, it would be positive, so that's increasing. And then here at 51, I'd have 200 minus 4 times 51. Let's see, what was that, -4, I think. So it's decreasing. So you see, it just works out. You got a maximum. You don't have to go through those steps, but just be aware that that is still going on there. That's why we get a maximum here. In other functions, you get a minimum when you do the critical number. So it all works out. Is that okay though? All right. Number 3. Another variation on this same type of problem. A rectangular area of 2,500 feet. So I've got a rectangle and its area is 500 feet, 2,500 feet square. And it's divided into 2 pins. The middle fence is parallel to one of the sides of the rectangle. So let me draw that instead of writing it down. You got it on paper there and out there. So I've got a rectangular area, but I'm going to divide it into 2 pins by putting the another fence down the middle, so to speak. Okay, so that area is 2,500. One piece of it. Find the dimensions of the rectangle. That would minimize the cost of the fencing. In other words, I want to minimize the fencing. As little of the fencing as I can get by with it. Well, all right. Now, we've switched gears here a little bit because I want to minimize the fencing. So I'm going to start here. My first equation is going to be the fencing equation. What is the fencing equation here? Well, if however you want to label it, L, W, X, Y. Let me use X and Y here just to change it up. There's no need here in this particular problem to make it, you know, don't call this one a variable and this another one. Just, it'll work fine if you just go with X all the way across. No need to separate the two, okay? So X is all the way across, Y is up and down. So what's the fencing I've got here? Well, I've got an X here and an X here. I've got 2 X's, don't I? How many Y's? 3 Y's. That's Y, and that's Y. They're all the same. It's a rectangle. See that? That's what I want to minimize. Now, what's my other equation in this case? The other equation is still the area equation. And that's the beauty of calling this X and that Y, because what's the area of this whole thing? It's just a rectangle, right? X times Y. Or length and width, if you want to call it that. Okay? Now again, like I said, we kind of changed gears here because what I know of these two is I know the area here. The area is 2,500, so A is 2,500. So kind of thinking through here things, I want to minimize this. Well, the minimum is going to occur at the critical number, the derivative, equals 0. But the problem is I've got X and Y. I can fix that problem over here, can't I? Solve this for Y, or X, doesn't matter. And then plug it in over here. So divide Divide here, let's divide by x. So we got 2,500 over x is my y. Now I can substitute that in for the other, the y in the other equation. So fencing F equals 2x plus 3 times 2,500 over x. Little adjustment there, so we got 2x plus, it's 3 over 1, so it'll be 7,500 over x. That's what I want to minimize. And now it only has one variable, and so now I can do the derivative. Because that's how I'm going to find this critical number, is get the derivative. And set it to 0. So the easy derivative here, that's 2. What's the derivative here? 7,500 over x. Probably I'd want to change, I mean, you do the quotient rule, but couldn't I write that as, let's make a secondary step here. Couldn't I say that's 7,500 x to the -1, then I can just use the power rule? Make the derivative easier. So it'd be 7,500, then just do the derivative off of that. So it'd be -1, x, subtract 1, so it'd be, that would be my derivative there. Yes? Which is 2 minus 7,500 x to the -2 So what am I doing here? Trying to find the critical numbers equals 0. That equals 0. Well, however you want to solve that, usually my suggestion is go ahead and flip that negative exponent over, make it positive exponent, so make it 7,500 over x squared. That equals 0. And the way I've been showing is, let's go ahead and multiply. To get rid of the denominator there, multiply by, both sides by that denominator. So that'll be 2x squared, that times that. And then that x squared times that, well, the x squareds will cancel, so that'll be minus 7,500. And then of course 0 times 0. Anything is still 0. So. Yes? One way to do it. So let's add the 7,500. 2x squared equals 7,500, divide by 2, next. X squared equals 3,750, I believe. So x would be plus or minus the square root of 3,750. However, we're talking about lengths and widths here. X is the length. Does the negative length make any sense? No. So it's positive square root of 3,750. That's what x is. Now also, pay attention to what it wants. In this case, it wants the dimensions to minimize the cost of the fencing. That's the x dimension, okay? So this would be the length that minimizes the cost of the fencing. X equal square root of 3,750. Well, I also need the other dimension, the y. So what about the y here? Well, I know y is 2,500 over x. So that'd be 2,500 over the square root of 3,750. And so those approximately are, square root of 3,750 is 61.23. This is 2,500 divided by that. $40.82. Those are feet, I believe. Gives you a rough estimate there. Now, one other thing, let me show you here, though, just FYI, and that's perfectly fine. That's probably how I'd have you give me the answer. But notice here, a little alternative form of this y. If I multiply by the square root of 3750, top and bottom, I get 2,500 times the square root of 3750 divided by square root, so it'll just be 3750. And notice that simplifies. Let's simplify that. It's 2/3. This right here turned out to be 2/3. Kind of interesting little side note. So y could also be listed as that. You might notice y is 2/3 of x there. It's okay.